Welcome students. In our last lecture we studied about the amplitude modulation techniques, generation and detection techniques, and advantages and disadvantages, applications of these. So after this we will discuss about the angle modulation. In angle modulation we will first discuss about the basic concept, then two types of angle modulation, the phase modulation and frequency modulation. Then we will discuss about relation between the phase and frequency modulation, bandwidth of these, and then generation techniques of narrow band frequency and phase modulation are other things. So first we for basic concept, if the frequency of any cosine function x of t is given by cos of omega c t plus theta 0, so it is equal to the omega c. It is a constant with the respect to t, and the phase of the cosine is constant. The angle of the cosine is theta t is equal to omega c t plus theta 0 is a linear relationship between with respect to t. So for other sinusoidal functions, the frequency may itself be a function of time, and therefore we should not think in terms of the constant frequency of sinusoidal, but in terms of instantaneous frequency of this sinusoidal, since it is not a constant for all time t. So this we consider an example. It is the equation given by this: y of t is equal to cos of theta t, where theta t is a function of time. Frequency y of t is case dependent on the function of theta t and itself be a function of time. So the instantaneous frequency y of t is given by omega I of t theta d theta t by dt. This is differential equation of theta t. As a checkup for this definition, we know that the instantaneous frequency of x of t is equal to the frequency at all times and is equal to omega c. Clearly, it satisfies the definition of instantaneous frequency where theta t is equal to omega c t plus theta 0 and omega t is equal to omega c. If we know the instantaneous frequency of some sinusoidal from minus theta to somewhat time t, we can find the angle of that sinusoidal equation, which is given by this equation. It is theta t is equals to integral of minus infinity to t omega t of alpha d alpha. So this is the the changing of angle theta t of some sinusoidal is the basis of two types of angle modulation, that is phase and frequency modulation. So first we discuss about the phase modulation. In this, the phase of the carrier signal is directly changed by the message signal. The phase modulated signal will be given by this equation: g of pm is of t is equals to a cos of omega ct plus kp m of t, where a is a constant, omega c is the carrier frequency, m of t is message signal, and kp, mainly this is the kp. The kp is the parameter that satisfies how much change in the angle occurs for every unit of change of m of t. So the phase and instantaneous frequency of this signal are this: theta of pm t is equals to omega ct plus kp m of t, omega I of t is equals to omega c plus kp dm by dt is equals to omega c kp m of t. So the frequency of phase modulation signal is proportional to the derivative of the message signal. Now we'll discuss about the frequency modulation. In this modulation, it changes the frequency of carrier, not the phase of any signal as in PM, directly with the message signal. Okay, the PM modulation signal is given by this G of Fm of t is equals to a cos of omega c t kf integral minus infinity to t m alpha d alpha, where kf is a parameter that specifies how much change in the frequency occurs for every unit change of m of t. The phase and instantaneous frequency of Fm is given by this. It is delta theta Fm is equals to omega ct kf integral of minus infinity to t m of alpha d alpha, and same expand this d by dt is integral m of alpha d alpha. This is omega c plus k of t. So this is the Fm and Pm. Now this is the frequency of Fm. We can see this. The frequency modulation is an instantaneous value of the information signal control the frequency of carrier wave. This is illustrated in the figure. So notice that the information signal increases, the frequency of carrier increases, and the information signal decreases as the frequency of carrier decreases. The frequency Fi of the information signal controls the rate at which the carrier frequency increases and decreases. As the AM Fi must be less than Fc, the amplitude of the carrier remains constant throughout this process. When the information voltage, in this we are transmitting the information, message signal. When the information voltage reaches its maximum value, then the change in frequency of the carrier will have also reached its maximum deviation above the nominal value. Similarly, when the information reaches a minimum, the carrier will be at its lowest frequency below the nominal carrier frequency value. So the information signal is 0, then no deviation of the carrier will occur. So now we discuss about this. Now we will discuss about the relation between Fm and Pm. Now the relation between the phase modulation and frequency modulation are tightly related to each other. From this equation, we see that the phase and frequency relations of Pm and Fm are given by the replacing m of t. M of t in the Pm signal with the integral of minus infinity to t m of alpha d alpha, whereas in the Fm signal replacing gives an Fm signal, and for replacing m of t in Fm signal by dm of t, this is we receiving the phase signal. It means we are generating the signal. If we are integrate the m of t signal by this, we will receive the Fm. Or similarly, when we differentiate the message signal, we receive the phase modulation of the signal. So now the figure shows the relation between the Fm and Pm. Now with the bandwidth of the Fm and Pm signal. The bandwidth of the different AM modulated techniques ranges from the bandwidth of message signal to twice the bandwidth of the message signal of DSBSC. When the FM signal were proposed, thought that their bandwidth can be reduced to an arbitrarily small value. It was discovered that the bandwidth of FM signal for a specific message signal was at least equal to the bandwidth of the corresponding AM signal. In fact, FM signal can be classified into two types. It is narrowband and wideband FM signal, depending on the bandwidth of the each signal. So now the bandwidth of narrowband signal is given by this. So bandwidth of FM narrowband, this is given by bandwidth of DSBSC is equals to twice of bandwidth of M of D. Similarly, we will see later when the conditions Kf, constant of Fm, is not satisfying the bandwidth of FM signal because higher than twice the bandwidth of the message signal. Similar relationship hold for the PM signal, that is G of PM narrowband is equals to A cos of omega ct minus Kp m of t sin omega ct, where Kp mode of Kp m of t is greater than 1. So the bandwidth of PM signal is bandwidth of DSBSC is equals to twice of bandwidth of m of t. So this is the discussed about the PM and FM. In next lecture we discuss about the generation techniques of narrowband and wideband PM and FM techniques.